I try to complete the two family, carbon and boron family. So you see the electronic configuration of the boron family is the ns2np1. In the S it has the 2 electron, in the P it has the 1 electron, unpaired electron initially 1, but if we excite 1 electron from the ns to P, then 3 unpaired electron we have, and valency is shown by the boron family is the 3. Boron is the non-metal, aluminium is the metal, but some property are similar to the boron. Gallium, indium and thallium are the metal. Okay, boron exists in the nature as the H3BO3 orthoboric acid, Na2B4O7.10H2O borax. Aluminium is the most abundant metal in the earth crust. It is present in the 8.7% by mass. It exists mainly as the cryolite Al2O3.2H2O and cryolite Na3AlF6 and bauxite Al2O3.2H2O. Okay, when we move from the boron toward the thallium, okay, what we have initially, we have in the boron only S and P subshell, but in the aluminium we have the D also. But when we move from the aluminium to gallium, again D, but from the gallium to indium, when we move again we have the change in the from the indium to thallium, again we have the change in the electronic configuration. Okay, in the boron and aluminium, electron are only present in the S and P. Okay, in the boron and aluminium, electron are only present in the S and P. In the gallium, electron are present in the D, and we know that shielding effect of the D electron is very poor. So what happens, these D's electron hold the outermost electron very tightly. Then indium also have the D electron, but when we move from the indium to thallium, what happens now? Again we have the extra F electron in the thallium, and these thallium attract the electron very strongly. So again the size and the property changes. So we have the large variation in the property of the boron family. Radius is maximum for the thallium, then indium, then aluminium, then gallium and then boron. Ionization energy 1 is maximum for the boron, then thallium, then gallium, then aluminium, then indium. Electronegativity, boron, then thallium, then indium, then gallium and then aluminium. Density, thallium, then indium, then gallium, then aluminium, then boron. Melting point, boron, then aluminium, then thallium, then indium and then gallium. Gallium melting point is very small, 303 Kelvin, means at the 30 degrees centigrade it is present in the liquid state. If we take the piece of the gallium in our hand, the energy of our hand is sufficient to melt the gallium into the liquid, means at the 30 degrees centigrade gallium is also present in the liquid state. Boiling point, boron, then aluminium, then gallium, then indium, then thallium. Now as I told you, due to the 3 unpaired electron, the valency is the 3, but down the group the tendency to excite the S electron decreases. This S electron cannot take the part in the chemical bonding, that become the inert. So due to the inert pair electron, valency decreases from the 3 to 1. Top element has the valency 3, but bottom element has the more stable valency as the 1. Top element show the oxidation number +3, but bottom element show the oxidation number +1. So due to the inert pair effect, down the group stability of the +1 oxidation number increases. Molecule of the boron and aluminium are the electron deficient, BCl3, AlCl3. Okay, these are the electron deficient molecule. They have the 6 electron in the outermost shell. They still have the tendency to attract the more electrons. So what they do, they always have the tendency to attract the electron to complete the octet. They work like the electrophore or Lewis acid. Then reaction with the air. Boron does not provide, crystalline boron does not provide any reaction with the air. Aluminium, okay, what it do? Aluminium form a protective layer of the Al2O3 on its surface. So this layer of the Al2 prevent the further oxidation of the aluminium. At the high temperature, amorphous boron can react with the air to give the boric anhydride B2O3 and boron nitrate Bn. B2O3 is typically acidic. Aluminium and gallium oxide are the amphoteric, but IN and TL oxide are the basic in nature. Next, reaction with the acid and base. Boron does not provide any reaction with the acid or base. Aluminium is the amphoteric in nature. It reacts with the acid also, it reacts with the base also. Then reaction with the halogen. Look, TLI3 cross means compound TLI3 cannot exist. Remaining element E, they react with the halogen X2 and give the compound like EX3, where X can be the fluorine, chlorine, bromine, iodine, and E are the member of the boron family. Boron has only one vacant orbital. So due to the one vacant orbital, the maximum covalency of the boron is the 4, or we can say the coordination number is the 4. But in the aluminium we have the third shell. In the third shell d orbital is also vacant. So boron cannot exceed the valency, but aluminium, due to the involvement of the d orbital, it can exceed its valency and it can show maximum coordination number up to the 6. Important compound of the boron family, first is the borax. Borax has the formula Na2B4O7.10H2O. The solution of the borax in the water give the NaOH, which is the stronger base, and orthoboric acid, which is the weak acid. So stronger base and weak acid, due to the stronger base present in the solution, the pH of the solution become the alkaline. Okay, then next, if we heat the borax, Na2B4O7, first from the 10 it lose the water molecule, and at the end, at the platinum wire, it will give a transparent glassy bead. This transparent glassy bead is used to test the different metal oxide present in the sample, and the whole process is called the borax bead test. For example, if we have the cobalt oxide and if we touch the glassy bead with the cobalt oxide and we heat in the oxidizing and reducing fluid, then it provide the blue color. So that's how we can identify that in the given compound cobalt oxide is present. Then orthoboric acid BOH whole thrice or H3BO3. Okay, although one can see we have the 3 hydrogen, so one can think that it can donate the 3H positive, but it is wrong. This boric acid is not the Arrhenius acid, it is not the Bronsted acid, it is the Lewis acid. It accepts the one lone pair from the water and give the BOH whole 4 minus and also release one H positive in the water. So N factor of the boron, N factor of the boric acid is not the 4, it is the 1. It only give the one H positive in the water. Then next reaction, heating of the orthoboric acid. If we heat the orthoboric acid, first is give the metaboric acid HbO2. On the further heating, it give the B2O3, that is the boric anhydride. Units of the boric acid are arranged in a sheet-like manner. Each oxygen and each hydrogen are able to give the hydrogen bonding. They arrange in a sheet-like structure. Next, we have the diborane. Diborane is one of the important compound of this family. Okay, what are the method of preparation of the diborane? 4BF3 plus 3LiAlH4. 3 is given, but it should be the 4. Give the 2B2H6 plus 3LiF plus AlF3. Next reaction, sodium borohydride plus iodine react together to give the diborane NaI and hydrogen gas. Next reaction, BF3 react with the sodium hydride to give the B2H6 plus NaF sodium fluoride. Diborane is the colorless toxic gas. As soon as it come in the contact with the air, it catches the fire. By the reaction, B2H6 plus 3H2 give the B2O3 plus 3H2O. B2H6 actually the combination of the two molecule of the BH3, and BH3 is the electron deficient. So it always have the tendency to accept the electron from the electron donor species or Lewis base. Suppose if we have the ligand tertiary amine, so what it do? This tertiary amine donate the lone pair to the BH3 and give the adduct. Similarly, carbon monoxide is the best ligand. It also donate the electron to the vacant orbital of the boron and give the BH3CO. Next, reaction with the ammonia. Okay, reaction with the ammonia, initially they give the ionic compound. Ionic compound on the further heating give the inorganic benzene. Formula is the B3N3H6, where boron and nitrogen present at the alternate position. In this reaction, hydrogen gas also release. This compound inorganic benzene is the aromatic in nature like the normal benzene, but not as stable as the real benzene because it is polar in nature. If we heat the inorganic this benzene further, it could also provide the inorganic graphite. The structure of the diborane, we know that in the structure of the diborane we have the banana bonding. Two banana bonds are there. Banana bond are also called the 3 center 2 electron bond. Okay, and banana bond length is the 134 picometer. Normal sigma bond is the 119 picometer. Normal sigma bond angle is the 120, but banana bond angle is the 97. The next reaction is the formation of the sodium borohydride or lithium borohydride. Metal hydride like NaH react with the diborane to give the NaBH4, and this NaBH4 is one of the reducing agent. We have already discussed this thing in the organic compound. Then carbon family has the electronic configuration NH2 NP2. In the P we have only 2 unpaired electron, but general valency of the carbon family is the 4. So what we have to do, electron of the S is transferred to the P. Then we have the 4 unpaired electron, 1 unpaired electron in the S and 3 unpaired electron in the P, and that's how the carbon family can show the valency 4. Okay, carbon is the 17th most abundant element on the earth crust. Silicon is the second most abundant. Okay, most abundant element on the earth crust is the oxygen. After the oxygen, Si. Germanium is the semiconductor quality of the metal. It is present in the traces amount, very less. Tin mainly present as the SnO2, that is called the tin stone, or cassiterite is the common name of the ore. Lead is mainly present as the PBS, that is the glena. Then next we have the family general properties. Okay, what is the property? First one, radius increases down the group. Second one, down the group ionization energy decreases. If we are moving from the carbon to lead, ionization enthalpy decreases, with the exception of what? Lead has the more ionization enthalpy than the tin. Then next, electronegativity. Carbon is more electronegative. Electronegativity of the Si, Ge and Sn is approximately same, and tin is also more, lead is also more electronegative. Electronegativity of the carbon is the 2.5. Si, germanium and Sn has the electronegativity 1.8 and lead has the electronegativity 1.9. Down the group melting point decreases, but again exception, lead has the more melting point than the Sn. Carbon, Si are the typically non-metal. Germanium is the metalloid. Tin and lead are the soft metal. They show the group oxidation number +4, but down the group, due to the inner pair electron, valency decreases. Then tendency of the +2, tendency to give the 2 valency increases down the group, and valency +4 is converted into the +2. So due to the inner pair effect down the group, the stability of the +4 oxidation, +2 oxidation number always increases. Okay, then reaction with the oxygen. Carbon family give the dioxide and monoxide. Carbon dioxide, silicon dioxide SiO2 and germanium dioxide GeO2 are the acidic, but SnO2 and PbO2 are the amphoteric. Monoxide they can also form. SiO is only obtained at the very high temperature, so we are not discussing the SiO here. Otherwise the carbon monoxide is the neutral, germanium monoxide is the acidic, and tin and lead monoxide are the amphoteric. Reaction with the water. Carbon, silicon, germanium, they don't react with the water under the normal condition. Tin react with the steam and give the SnO2 and 2 hydrogen. Tin is above the hydrogen in the electrochemical series. So above one can act as an anode, lower one can act as a cathode, and tin can donate the electron to the hydrogen. The next, reaction with the halogen. Look, they can give two type of the halide, MX2 us halide and MX4 ic halide, like PvCl2 plumbous chloride and PvCl4 is the plumbic chloride, but carbon cannot react directly with the halogens. Among these one, SiCl2 is important. Si is connected to the 4Cl. It undergoes the hydrolysis reaction and all the 4Cl now replaced by the OH, and that is called the silicic acid, SiOH whole 4. Next property, carbon has the excellent property to give the pi bonding. Okay, it shows the p pi bonding, carbon pi bond, carbon oxygen pi bond, carbon nitrogen pi bond, carbon sulfur pi bond, carbon even phosphorus pi bond. Carbon has the excellent property to give the carbon pi bond. Catenation property of the carbon is also highest. Maximum catenation shown by the carbon, then Si, then germanium and indium. Same property of the catenation, lead cannot show the catenation. Allotrope of the carbon, diamond is the most important allotrope of the carbon. Each carbon is the sp3 hybridized with the bond angle of the 109 and 28 minute, and bond length is the 154 picometer. It is a natural hardest substance, so that's why it can be used as a abrasive. Okay, next is the graphite. In the graphite, each carbon is the sp2 hybridized. They have the 6-member honeycomb like structure, and these layers are connected by the weak van der Waals force of attraction with each other. Then carbon sp2 carbon bond length is the 141.5 picometer, and the distance between the two layers is the 340 picometer. Okay, the fourth electron of the carbon is present in the pure p orbital, that is free for the motion, that is free to move throughout the sheet. So that's why the graphite conduct the electricity. Graphite is very soft and slippery in nature, so that's why graphite is also used for the dry formation of the dye lubricant purpose. Then carbon monoxide, if we heat the carbon in the limited supply of the oxygen, it gives the mainly carbon monoxide. Formic acid on the dehydration, H2SO4, concentrated H2SO4 is the dehydrating agent. If formic acid heated with the H2SO4, concentrated H2SO4, dehydration occurs, that gives the H2O plus CO. Next, carbon with the steam, red hot carbon with the steam. If we pass the steam from the red hot carbon, what they give? They give the mixture of the 1:1 carbon monoxide and hydrogen gas, that is called the water gas. If in place of the steam we use the air, then red hot carbon with the air, that give the mixture of the carbon monoxide and the nitrogen, that is called the producer gas. Carbon monoxide is the strongest ligand. If suppose someone take the breathe in the surrounding of the carbon monoxide, then carbon monoxide replace the oxygen and form the 300 times more stable complex with the hemoglobin. So slowly all the position of the hemoglobin are replaced by the carbon monoxide, and now carbon monoxide connected to the hemoglobin. So after some time there is no more free space available for the oxygen. So what happens under such condition? The one can be die also, so it is poisonous gas for us, and it is also used in the metallurgical purpose. I have told you already, if temperature of the metallurgical operation is the less than 710 degrees centigrade, then it is the carbon monoxide is the better reducing agent. If temperature is more than that 710 degrees centigrade, then carbon is the better reducing agent. Then carbon dioxide, if we heat the carbon in the excess of the oxygen, then that gives the carbon dioxide. Fuel, any hydrocarbon CXHY, if heated with the oxygen, then that also give the CO2. CaCO3 is the base, HCl is the acid. If they react together, then acid base neutralization occurs to give the CaCl2 plus H2O plus CO2. Then if we take the whenever we take the oxygen inside the body, it burn the glucose. Due to the burning of the glucose, we have the formation of the CO2 and H2O. CO2 is partially absorbed in the body with the water, and CO2 and water can give the H2CO3. H2CO3 is the carbonic acid dissociate one time to give the bicarbonate. Then in the blood we have the buffer mixture of the H2CO3 and HCO3 minus. This H2CO3 and HCO3 minus buffer is very important to maintain the pH of the body, to maintain the pH of the blood. Okay, then one more important, CO2 also utilized in the photosynthesis reaction. CO2 plus H2 in presence of H2 and photosynthesis, they give the glucose and oxygen. At this point I have written the CO2, but it is not the CO2, it is actually the 6O2. Okay, so 6CO2 plus H2O, they react together to give the 6CO2 plus glucose. This is the method by which the plants can produce their food. Then CO2 is also the greenhouse gas. It is responsible for the global warming. Solid ice is also called the dry ice. It is used for the cold storage purpose. Then next we have the compound SiO2, silicon dioxide. Silicon dioxide is, this compound is unreactive. It does not react with anyone. It is generally silica, which we have everywhere available. It does not react with the anyone else except the NaOH and HF. When Si react with the NaOH, it gives the sodium silicate. Sodium silicate is the one of the component of the glass industry, glass formation. And SiO2 plus HF, they give the SiF4 plus H2O. This reaction, second reaction, is used for the etching of the glass. Silicons are the organic polymer of the silicon. What they do, look in this one, what we have the some chlorine linkage. It may be the 1, it may be the 2, it may be the 3. On the hydrolysis, these chlorine linkage replaced by the OH. Then on the polymerization, water molecule lose and they give the straight type, or maybe the branch type, or maybe the, means it depend upon the how many Cl we have. It give the several type of the polymers. Those are called the silicons. Silicons are the bad conductor of the electricity. They are inert material, don't provide any reaction with anyone. So they are used for the gasket, they are used for the silicone surgery, plastic surgery. Then we have the silicate. Silicate has the simple formula SiO4 4 minus. This is called the ortho silicate. If two oxygen are connected with each other, that give the pyrosilicate. Sorry, if one oxygen joined with each other, that give the pyrosilicate. If two oxygen connected with each other, that give the chain silicate or cyclic silicate. If 3 oxygen shared, that give the sheet like silicate. If 4 oxygen shared, that give the 3D silicate. Okay, then zeolite are the shape selective catalyst, and chemically these are aluminosilicate. We know that structure of the silicate, each Si tetrahedrally connected with the 4 oxygen, and each oxygen is connected with the 2 Si. If in this 3D structure, if some molecules of the Si replaced by the aluminium, then that structure is called the aluminosilicate. Okay, if some molecule of the Si replaced by the aluminium, then that structure is called the aluminosilicate, and its common name is the zeolite. Okay, these are the shape selective catalysts. They have the porous structure, we can control the porosity. The important zeolite are the ZSM5. What is the important? It converts the alcohol directly into the gasoline. Okay, this ZSM5 very important, several times it is given in the NCERT at the different chapter. It converts the alcohol directly into the gasoline. And then is the sodium zeolite. Sodium zeolite is used to remove the hardness of the water. In the hard water we have the Mg+2 and calcium +2. Sodium zeolite react with the calcium +2 and sodium replaced by the calcium. What they give? Na2Z plus Ca+2 give the CaZ plus 2Na. And now in the water we have the Na+2, and due to the presence of the Na+2, water is not the hard. So that's how we can remove the hardness of the water by this method. Okay,